Web Systems, Week 7, Computer Science 1, Part 3, Number Systems. From the last two lectures we learnt about computer architecture and data representation, like ASCII and Unicode. This week we're going to talk about numbers and converting them. Now all these pulses represent numbers, because essentially that's what a computer is, a giant number crunching system. We call these things numeral systems, and sometimes we're also called a number system. So the numeral systems that we typically see are things that we see every day, like decimal. But we also see things like binary, octal, and hexadecimal. The most common numbering system we see out there is what they call the Hindu Arabic. It used to be called Arabic, but technically it actually came originally from India. And it's a positional system. So the base, in case of decimal, is base 10, binary it's base 2, and you can use practically any integer base whatsoever. In computing we tend to use powers of 2 simply because 2 is represented as 0 or 1. So what is this magic thing called a base? Well, it simply says the number of digits we have. So for base 10 we've got digits 0 to 9. If we've got base 8 we've got digits 0 to 7, assuming we're using Hindu Arabic type numbers. And typically we put a little subscript down here to represent the base. An important thing to notice is in decimal it's always base 10. We usually omit the 10. In other words, we don't need to say it because we know what it is. Unfortunately, it means if we've got something like octal, we have to know whether it's octal or decimal. In fact, even things like binary, we should have an indication that it's binary. Now, when it comes to programming, for example, we don't have special lowercase or what we call subscript characters, so we have to represent them either a prefix or a postfix. For example, hexadecimal could be represented in two formats, 0x and 1, 2, 3, or 1, 2, 3 with a H at the end. One of these two options are perfectly fine, depending on the context you're using it in. For example, in HTML, hex is represented with a hash symbol, hash 1, 2, 3. Now we already know about base 10. It uses 10 symbols, 0 to 9. The decimal system is very positional, so it's really critical to know exactly which position you're in. The position actually indicates the power of the base. For example, let's look at 45. That's simply 5 plus 40. 10 to the 1 is 10. 10 to the 0 is 1. So 4 times 10 equals 40. 5 times 10 is 5. And the answer is 45. Simple as that. Here's another classic example. 2 times 10 to the 2 is 2 times 10 to the 2, which is equal to 2 times 100. It's equal to 200. Same thing with this. 3 times 10 to the 1, that's 30. And of course that's 4, which is our 234. Base 2 is very similar to decimal, except for one thing. There's only two digits, 0 and 1, that are valid. So, for example, 10, it's not 10. It represents 2 plus 0. In this case, 1 times 2 plus 0 times 1, that's equal to 2 plus 0, which is equal to 2. Easy. 1101, well that represents 1 times 2 to the 3, which is equal to 8. 1 times 2 to the 2, which is 4. 0 times 2 to the 1, so that's 0 times 2, which is equal to 0. Plus 1 times 1, which is 1. So 8 plus 4 plus 8 plus 4 plus 1 equals 13. This leads me to a classic joke you'll see on Computer Science Geek t-shirts. There are 10 types of people in this world. Those who can read binary and those who can't. Let's see how well we can memorize what the binary, what powers of 2 are.
1 is for one sign-in to rule them all, OpenID. 2 is a version of the interwebs waiting to call. 4 is the sum of 3 kids and a guitar. 8 is for the IE currently in beta. 16 bits was so 90s, vids and pics of 16-bit games. 32 is the integer of version 4 IPs. 64 is unseen to gamers. 128 is a team of genetics researchers. 256 is a change of routine and an artistic journey. 512 is A-OK in finger binary. Only problem here is that while many places use the pinky finger, Wiki uses the thumb. Easy to alter though? Suggest this little piggy. 1024 by 768 is the web's minimum display. 2048 is Intel's guess of an impending singularity. 4096 is how many noodles from 12 twists. 8192 into eBay brings up the weirdest of lists. 16,384 got 2,322,573 into the Prime database with a bit of skill. 32,768 according to Googleism is probably overkill. 65,536 last year made Microsoft's cheeks beam. 131,072 cores support for cactus code on Blue Jean. 262,144 caused Apple legal sparks. 524,288 is the nerdiest of all hit landmarks. 1,048,576 is 1 megabyte precisely. 2,097,152 is a windshield wiper pattern number, bizarrely. 419434 will get you almost to Mongolia, Google Earth. 8,388,608 into Google brings up many a failure. 16,777,216 choices to choose from each day. 33,554,432 is the number of people over 25 generations helping you to be here watching this today.
So let's see, what other type of number systems are there we see outside in the rest of the world? And how come they're different from binary and decimal? Well, obvious thing is Roman numerals. Let's take a look. What's 1 in Roman? It's easy. What's 3 in Roman? That's so easy. What's 4? That's actually a strange subpositional thing. That's actually 4, and then we have 5, and we have 6, and so on and so on. And we have 9, we have 10. Do you notice this is actually a subtractive system? 5 minus 1 becomes 4. 10 minus 1 becomes 9. It's a crazy system. What about imperial measures like inches, feet, pounds and clocks? Good example is, there's 12 inches is 1 foot. Now what the heck does that mean? I don't know. What about clocks? The old classic clock. That's 5 p.m. That's 11 p.m. And then it cycles around. 12, we have noon, or midnight actually. Then 1 o'clock, 2 a.m. and so on. It's an irregular system. Everything seems to be based in powers of 12 for some reason. So it's a slightly different number system, and again, your coding has to deal with different things. Internally though, a lot of this is stored digitally, and you convert them from the digital format into this imperial measure, or clock time measures. Now what can we use these binary numbers for, apart from calculations, like additions, subtractions and so on? You saw from the previous lecture that they can represent data, and a good example is ASCII, which basically letters are being represented by numbers. So for example, A, it's decimal 65, and which actually represents this sort of sequence in binary: 1 0 0 0 0 0 1. And if you lowercase it, let's take a look at this example. B, that's simply the next one on. C, for example, would be 1 0 0 0 0 1 1. It would be C. And the interesting thing about ASCII is they have a special flag. This little digit here, 2 to the 32, the 5th place, it actually means if you add 32, you'll get the lowercase version of the number. So simply, if you want to convert, for example, C to a lowercase c, becomes 1 1 0 0 0 1 1. Simple as that, which happens to be 99 decimal. So you can easily convert upper lowercase by adding or subtracting 32. And one simple example of using ASCII and binary numbers. 2 to the 5, the fifth bit, indicates if it's lowercase or uppercase. Simple as that. Now, big issue we have with binary is it's hard to represent even any middle-sized numbers without a lot of digits and possibly a lot of zeros and a lot of ones. And as humans, we can't really see this. Computers don't really care. So a very common thing we see in the computing world is hexadecimal numbers. We often call it hex, but technically hex is not correct because hex represents 6, as in hexagon, I mean, my apologies. And it's often used as a shortcut for binary. So let's take a look. Here is the equivalent of what we call hexadecimal table with decimal and binary. Notice at 9 we don't jump to 10, we insert our own symbol. So A represents 10, F represents 15. So just keep that in mind. For some reason we've chosen to use A, B, C, D, E, F, but it could have been other things as well. But luckily we just stick to the alphabet. What happens if we go over that one digit? This is an example. 1 0. Well, we simply plug on an extra digit, and what we get is 16. What if we've got FF, two sets of digits? Well, again, FF represents 1111, which represents 255. Very useful to memorize these, and I'll show you why later. Now, it turns out that every hexadecimal digit represents 4 binary digits. Very good for simplification. I presume you've all done networking at one point. Well, the UTS handbook, its address on the internet is this magic number. A bit too long for me to pronounce off the top of my head. About 2.316 billion. Well, that actually represents, in binary digits, a long sequence of digits, which is pretty hard for us to read. So we can convert that to what we call dotted quad format. So that becomes this: 25, 16, and 55. In other words, the classic 138.25.16.55, that represents the UTS handbook. Now the problem is we're now going to what we call IP version 6, so it's 128-bit addresses instead of 32 bits. That means the number of digits is really, really long. It happens to be something like 42 billion, or also known as 42 undecillion, or something like that. Quite frankly, a bit hard for me to work out. From 4.2 to 10 to the 37. Okay, and in binary, it's 126 digits. Awfully difficult to look at. We could convert that to hex, which is 2002 ... and so on. And good thing about IP version 6, you can simplify that even further by simply taking every group of 4 digits. That becomes a single 0. And 137, 289, 2002. So you can kind of vaguely read it, and it's easier to type that in than that humongously large number we saw previously. We've also seen hexadecimal with HTML. Good example, colors. Here we've got an example of a color, FF0000. Now it turns out that colors in HTML are in a group called RGB, red, green, blue. So in this case, the first 2 digits are red, second 2 digits are green, and the last 2 digits are blue. Okay, and the different values represent how red and how blue it is. So 0 says it's got no red, no green, and a full-on blue. And you can have shades of that. Here's an example. Yellow. That's full on red plus full on green, no blue equals yellow. If you want some in-between colours, you simply put halfway values. For example, we've got white, which is full on, full colours, and black, for example, would be 0, 0, 0, 0, 0, 0 for black. If we want grey, we would simply say 8, 0, 8, 0, 8, 0, because 8, 0 is halfway between, roughly halfway between FF and 0, 0. Try it out, it becomes grey. Another shortcut we've seen is octal. Octal is base 8, simply represented by each digit represented by 3 bits. For example, Chmod, we've seen that from Linux Gym Chapter 2. Chmod 777, well, that's equal to read, write, execute. Okay, so each one of these bits represent whether it can be readable or writable, executable. So let's take a quick look. 777, that means owner can read and write execute, the group can read, write, execute, and the public can read, write, execute. That's normally not a good combination to have in any file, especially if it's your home directory, because your fellow students could then hack. And I hate to say you, there are plenty of students who've done this. This is not good practice, because it means anybody on the system can overwrite your public HTML, and that's how you get hacked. Let's try another one. So what does 751 mean? Let's try it out. Well, obviously 751, that's equal to, in binary format, 111. The 5 is 101, and the 1 is 001. Let's take these digits, work it out. That becomes WX, RX, and dash dash X. In other words, owner, read, write, execute, groups, read and execute, and others can only execute. It could be an executable file. That means that nobody can read your shell script if they use it publicly. So it's a good example of what octal and binary can be used for. So we've seen it all. Let's take a look. We now know decimal. It's base 10. You have basically 10 symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, fairly straightforward. And binary again is 0 and 1. And hexadecimal, we've used A to represent 10, B to represent 11, F to represent 15. Really obvious. So the generic rule, any number at particular base B, you need B symbols. So we've got a base 26 system. We'll be represented as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, dot, 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 until we have 26 symbols listed in the system. So, quick exercise. How many symbols? We've got base 5. Fairly obvious. The answer is 5. How many symbols have it got? 11. Fairly obvious. 11. Trick question. We're not restricted to using numeric digits to represent symbols for a number system. For example, this could be a hypothetical one. Exclamation mark could represent 0, at sign represent 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the base? Let's count the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is base 10. Would you believe it? It turns out to have 10 symbols, so it's base 10. So what would the decimal value of this funny thing be? Exclamation mark, and let's curly bracket. Let's take a look. That is 0. That is 9. So the answer is 0, 9, which of course is equal to 9. A weird thing, if you gobbledygook, that could possibly be because it's encoded differently. Another example is it could be Chinese. For example, 1 could be, that could be 2, that could be 3, that could be 4, and so on. It doesn't have to be digits. and you'll get to do some of these things when we look at the conversion section in the next lecture.